Okay, so previously we have covered so many things in cyclic groups, like their definition, their generators, order of their elements, the subgroups of cyclic group, and so much. And now we will talk about the exercises. So to begin with a simple one, we say that for find all generators of Z6, Z8, and Z20 solution. So let's say for Z6, we have generators of, now what are the generators? The generators of a cyclic group or Zn in this case are those elements which has order with the order of the group. The order of the generator and the order of the group have GCD1. So that are 1 and 5, because GCD of 6, 1 is 1, GCD of 5, 1, sorry, 6, 5 is 1. Now, remember the definition. Now I'm going to write only the generators. For Z8, we have 1, 3, 5, and 7. For Z20, we have 1, 3, 7, 9, 11, 13, 17, and 19. Perfect. Question. Suppose that the set generated by A, B, and C are cyclic. Groups of order 6, 8, and 20, respectively. Okay. Find all generators of A, B, and C. Now, this is same is this has same answer as the question number 1. So because Zn is also a cyclic group, so in solution, what can you write is that, but we have the different notation now. So for A, we have A and A power 5 is the generator. For B, we have what? For Z8, what we had? 1, 3, 5, and 7. So we have A, sorry, B, B cube, B power 5, and B power 7. And for C, we have C, C cube, c power 7, c power 9, c power 11, c power 17, c power 9p. And that's it. Perfect. Now, list the elements of subgroups. List the elements of subgroups generated by 3 and generated by 7 and u of 20. Perfect. Now, the solution will be simple as that. What do you need? 3, 3 square, 3 cube, 3 power 4, and that is nothing but 3, 9, 7, and 1. Okay? And 7, it should be 7, 7 square, 7 cube, 7 power 4, and that is going to be 7, 9, 3, 1. Okay. Now, then number 4 is in Z24. First, we need to find a generator for the intersection of say generated by 21 and the set generated by 10. Now, suppose that there is an element A which has order 24. Now we need to find a generator for the set generated by A power 21 intersection A power n. And in general, what is a generator for the subgroup generated by A power m intersection A power n. Okay, bit long one, but worthwhile doing because it's interesting. So we have Z24. Okay, and so we will say that the set generated by 21 will have elements which is 0, 21, 18. If you compute the addition modulo n, modulo 24, you would get these elements 12, 9, 6, 3. And the set generated by 10 is 0, 10, 20, 6, 16, 2, 12, 22, 8, 18, 4, 14. Now, since by the fact the intersection of two subgroups is a subgroup according to the proof of theorem 4.3, we can find a generator of the intersection by taking the smallest positive multiple of 1, smallest positive multiple of 1 that is in the intersection. So the intersection have element, this intersection is generated by 6, because if you look at the intersection, the intersection is going to be 0, 0, and then if you look 21, there is no 21 in 10, 18, there is 18. If you look, there is 12, there is 12, there is 6, there is 6, and 18 and 15, there is no 15 here. 3, there is no 3, 9, there is no 9. So so this is nothing but 0, 6, 12, 18, 24 is 0 itself. So this is it. Okay. Now similarly, for the second part, when the order of A is 24, and you need to find a generator for the intersection of A, say generated intersection A21 and 18, you would get what? By using the similar kind of theory, you get right, and the elements will have 0, a power 6, a power 12, a power 18. That's it. Now for the case, in general, for the case a power m intersection a power n, we let that a be the LCM, least common multiple of m comma n, and we write that a is equal to m product s, and a is also equal to n product t. Then a power k is equal to a power m power s, which belongs to the set generated by a power m, and a power k is equal to a power n power t, which also belongs to the set A generated by a power n. So a power k, set generated by a power k, is in the intersection. This is a subgroup inside the intersection. Now this proves one side. Further, now let a power r be any element from the intersection then r is a multiple of both m and n. Follows that r is a multiple of k. So a power r is also in the state generated by a power k. And this proves the other side. And then you can say that the generator of the intersection is a power k. Perfect. Now, let me find an interesting one. Okay. So we were at number 4. Number 5. Number 5 is prove that an infinite group must have an infinite number of subgroups. Interesting. Solution. So this is all theory. So an infinite group had only finite subgroup number of subgroups. Subgroups, then it would have only a finite number of a finite number of cyclic subgroups. Each of these, if each of these cyclic subgroups is finite, then the group would be finite. Finite since every element is in the cyclic subgroup generated by itself. So the group contains at least one infinite cyclic subgroup. Okay, and we call it generated by A. Then the subgroups generated by A square, A cube are distant subgroups. Since the least positive power of A in A power I is A power I itself, and A power I is not the least positive power. Positive power of A in any subgroup. In any subgroup, A power J, for J not equals to I. Hence, it has infinite subgroups. Okay. Now, the other one is, let's say it's number 6. We say that let P be a prime. Okay. Or if a group has more than P minus 1 elements of order P, Y can't be the group, Y can't the group be cyclic? Okay, this is the question. Now everybody knows, like we know that the cyclic group of order P should have P minus 1 elements. And now this is the statement. The other way is towards an infinite cyclic group does not have element of prime order, a finite cyclic group can have only one subgroup for each divisor of its order. So a subgroup of order P has exactly P minus 1 elements of order P, and another element of order P would give another subgroup of order P. And that's why the group can't be cyclic. Right? Okay. Now, we have I guess we should end this part here. Thank you so much.